In this lecture, we'll cover actually calculating delta S values for various reactions, and then we'll go on in a second part to introduce the free energy change, delta G, for prediction of reaction spontaneity. Before we do any of that, we need to briefly state what we call the first, second, and third laws of thermodynamics. The first law of thermodynamics, which is discussed in first semester chemistry, and for us it was discussed in the first couple lectures of this module. Energy is conserved. It can neither be created nor destroyed. Any energy lost by the system is gained by the surroundings, and vice versa. The total energy of the universe is constant. And another way of stating this in first semester chemistry was that the change in internal energy for a reaction or process is equal to the heat flow plus the work done. The second law of thermodynamics states that any spontaneous reaction or process will result in an increase in entropy of the universe. So we write that as delta S of the universe being greater than 0. If you recall, we defined the universe as the sum of the system, typically the reaction we're looking at, and the surroundings, everything else. Therefore, the change in entropy for the universe is the sum of the change in entropy of the system and its surroundings. So we'd write that as delta S of the universe equals delta S of the system plus delta S of the surroundings. The second law of thermodynamics simply states that the sum of the delta S of the system and the delta S of the surroundings, the total entropy change for the system plus the surroundings, has to be greater than 0 for any spontaneous reaction or process. In other words, a spontaneous reaction or process results in an increase in entropy of the universe. We will invoke the second law of thermodynamics when we introduce free energy change, delta G, in the second part of this lecture. How about the third law of thermodynamics? The third law of thermodynamics will help us actually calculate values of delta S for reactions and processes because it defines what an entropy of 0 would mean. The entropy of a perfect crystal at absolute 0 temperature, 0 K, is equal to 0. So this gives us a baseline to base entropy values for all the substances that we're familiar with. Recall the Boltzmann equation. Entropy equals the Boltzmann equation, Boltzmann constant, times a natural log of the number of microstates available to the system. Well, the atoms in a perfect crystal at 0 K would have only one possible arrangement, or a microstate. So in that case, the number of microstates equals 1. Since the ln of 1 is 0, then the entropy is 0 for a perfect crystal. And again, this gives us a basis for calculating the magnitude and sign of delta S for any particular reaction or process. So let's get into calculating delta S for reactions. Since the third law establishes that the absolute entropy of a perfect crystal at 0 K is 0, the value of S, the entropy value for any substance above 0 K, will be a positive number. If you think about it for a second, that makes perfect sense. Higher temperature, anything above absolute 0, plus more possible microstates for complex structures would produce an increase in entropy compared to the perfect crystal. Methods for determining these absolute entropies are not our business in this course. However, we can use tables of entropy values. They're actually called standard molar entropy values. which would be the standard entropy value for 1 mole of a substance at 298 K, and this information is readily available. What I've done here is I've constructed a table of substances noting what phase they're in, what state they're in, and their standard molar entropy values. Notice the units are joules per mole per K. A lot of these values are from the table that's available in the textbook that accompanies the course, but I did bring in other values that I needed for the examples we're going to cover. So let's look at some observations about these entropy values. The table lists the entropy of water in the gas form, water in the liquid form, and water in the solid form, ice. It's about 188 for the gas form, around 70 for the liquid form, and around 41 for the solid form. So you see the entropies dropping as you go from a gas to a liquid to a solid. Now this makes perfect sense because you'd expect the disorder to decrease, in other words, order to increase, going from gas to liquid to solid. So it's not surprising that in this series, the solid water, ice, would have the lowest value of standard molar entropy. How about comparing N2O5 gas, which is right here on the table, with NO2 gas, which is right here, 346 compared to 240. Now, this makes sense also because N2O5 has a more complex structure than NO2. So not only would there be more available microstates positionally from the stretching and the bending of all the extra bonds in N2O5, but more opportunity for randomized energy dispersal. And finally, one more observation I just want to point out. It's not all that big of a deal, but if you'll notice, the entropy of oxygen, which is 205 in the gas form, appears to be higher than the standard molar entropy of nitrogen, which seems to be higher than that of hydrogen. So it seems like in the series of diatomic molecules, entropy appears to decrease with decreasing molecular weight. Now, since entropy is a state function, meaning it's not dependent on the exact pathway taken from the initial to the final state, we can determine a deltaS, the change in entropy, for any chemical reaction by simply calculating the difference between the total entropy values of the products, final state, and the total entropy values of the reactants, the initial state. So mathematically, we can determine deltaS, actually the change in standard entropy, with an equation that looks very much like what we used for determining standard enthalpy changes. We'll sum up the entropy values of all the products, multiplying by the number of moles of each, and subtract the sum of all the entropy values of the reactants, multiplied by the number of moles of each. Let's look at some examples of using this equation. And to do that, we'll look at 4 examples. These are examples that we looked at previously. 3 of them were spontaneous, 1 was non-spontaneous. So our first example here is our now well-known reaction of hydrogen and oxygen to give water molecules. And of course, we noted previously that this reaction was quite spontaneous and exothermic. Delta H is quite negative. Now, we can calculate a standard entropy change by adding up all of the entropies of the products. Now here, the only product is water in the liquid form, but we have 2 moles of water in the liquid form. So we have 2 times 69.91 joules per K per mole. And of course, I got that off the table on the previous slide or from the table that's available in a lot of textbooks. And we're going to subtract the sum of the standard molar entropies of the reactants, 2 moles of hydrogen gas times 130.58 joules per K per mole, and 1 mole of oxygen gas. We want to remember that the liquid state in the equation specifies the liquid state, so we want to make sure that we're using the liquid state value from the table. When we cancel out units here, we're left with joules per K, and if you do this carefully, you take 2 times 69.91 and leave it in this bracket, 139.82, and then you subtract the sum of these two, so we have subtracting here the sum of those two. So basically we have 139.82 minus 466.16, or minus 326.3 joules per K. Now the minus sign means that we're creating order, or in other words, we're producing less disorder. If you look at the reaction itself, this is pretty logical. You've got 3 moles of gas on the left, 2 moles of liquid on the right. So definitely when you go from left to right, you're producing a lot of order. It's not surprising that delta S is negative. So this reaction is spontaneous, and we know it's spontaneous because we can observe it, despite the negative delta S, because remember, a negative delta S does not favor spontaneity. Reactions don't naturally go in the direction of increasing order unless there's a reason to do it. So apparently here, this reaction is spontaneous because of the dominating effect of this large and negative enthalpy change. Keep in mind here that the units that we're using currently for delta S are joules per K, and those for enthalpy are kilojoules. Now we'll examine the reconciliation of those two different units pretty soon, especially when we get into talking about free energy change, delta G. Let's move on and look at some other of our example reactions. How about the reaction of nitrogen and oxygen to form nitrogen dioxide? Previously, we said this reaction was endothermic. It has a delta H of plus 67.68, and that experimentally it's determined or observed to not be spontaneous. Let's calculate delta S for this reaction. When we do that, we end up with a value of minus 120.6 joules per K. Well, does the negative sign here make sense? Sure. We've got 3 moles of gas on the left in the reactants, but only 2 moles of gas on the right. That means that we're creating some order, or we're producing less disorder, so it's not surprising that delta S is negative. So it's not surprising that this reaction is just not spontaneous. It does not have a favorable enthalpy change. It's positive. You have to absorb heat from the surroundings to get it to go. And it's going in the wrong direction entropy-wise. It's creating order. With both of those things working against you, it's not surprised the reaction's not spontaneous. How about this? Is what we've been calling this is a process rather than a reaction. But in any event, the melting of ice to water at room temperature, we noted before that this is endothermic. It has a positive enthalpy change. And despite that, it's spontaneous. Well, why? Well, you can see going from solid to liquid, we should be creating some disorder. So you'd assume that the entropy change is favorable. If we actually calculate the number, being careful to use liquid water where we're supposed to use liquid water and solid water where we're supposed to use solid water, we get an entropy change of plus 29 joules per K. So the entropy change is favorable going from the ice to the liquid. That seems reasonable. So since it's common knowledge that this process is spontaneous, we'd say here that this must be entropy driven because the enthalpy change does not favor spontaneity, but the entropy change does. Overall, if we observe spontaneity, it must be driven by the entropy change. Finally, let's look at this reaction of solid N2O5 going to NO2 and oxygen. Again, we noted previously that this reaction was endothermic. It has a very large and positive deltaH, but we said it was spontaneous. So we know that this reaction must also be entropy driven, and just by observing the reaction and the way the phases are marked, this does make sense. You're going from a solid to 5 molecules of gas. So there's an incredible amount of disorder created going from reactants to products. We can calculate an actual number for deltaS. Again, being careful about bookkeeping here. And we get a deltaS term of plus 811 joules per K. So on the, just in comparison to some of the other deltaS values we calculated, this is fairly large, and it's fairly large in positive. Again, not surprising, you're producing 5 moles of gas from 2 moles of solid. So if this reaction is spontaneous, this must be entropy driven because the deltaH term is certainly not favorable. So let's try to summarize what we know about these 4 examples, 3 reactions, 1 process at 298 K. Here are our 4 reactions in 1 process. I'll fill in the deltaH values. So for hydrogen and oxygen, the reaction's quite exothermic. deltaS here is negative, so we say there's decreasing entropy. Experimentally observed, this is quite spontaneous, so our conclusion is that this reaction must be enthalpy driven because the deltaS term is negative, meaning you're creating order that does not favor spontaneity, so it must be driven by this large and negative deltaH. How about the reaction of nitrogen and oxygen? Well, that's endothermic. That's not good for spontaneity. deltaS is negative. That's not good for spontaneity because you're creating order. So it's not surprised that experimentally it's observed that this is not spontaneous. And we say both the enthalpy and entropy terms do not favor spontaneity. How about the melting of ice to water? Well, it's endothermic. It absorbs heat from your hand if you're holding that ice cube. But the deltaS term is favorable. It's positive because you're creating disorder. We know this is spontaneous, so this process must be driven by the entropy change. Finally, the reaction, or we could say the decomposition of N2O5 solid to NO2 and oxygen, it's incredibly endothermic. It absorbs a lot of heat. It has a very favorable entropy term because you're creating a lot of disorder, and ultimately it's the entropy term that drives this reaction because the enthalpy term certainly does not. One thing you might want to notice here that could bother you and actually should bother you is that we're kind of comparing apples to oranges here. You'll notice that we've got kilojoules for deltaH and joules per K for deltaS. So again, we're going to reconcile these when we start talking about delta G and free energy changes in part 2 of this lecture. For now, all we needed to know was whether deltaS was negative or positive and know the experimentally determined result. So for example, for hydrogen and oxygen. Of course, these are not in exactly the same units, but we know this reaction is spontaneous. We know that the entropy term is negative, which is not favorable to spontaneity. Delta H is negative, which is favorable. So we say this is enthalpy driven, irregardless of whether or not we've reconciled these units exactly. So we can more precisely take into account the magnitudes and signs of delta H and delta S, and ultimately the reaction temperature, in predicting reaction spontaneity by introducing the concept of free energy change, delta G, which is on the next slide, which we'll save for part 2 of this lecture.